Rate of change using the chain rule. Hello everyone. Let's begin our lesson on the rate of change using the chain rule. To start, let's recall our previous section, where we discussed the fundamental process of finding the rate of change of a dependent variable with respect to an independent variable. However, in many real-world scenarios, the relationship is not that straightforward. We often encounter situations where two different variables, x and y, both depend on a third variable, which is typically time, represented by the letter t. In such cases, we might find that we cannot directly relate x and y through a simple, single function. But don't worry, we can still determine how y changes with respect to x by utilizing the chain rule. In the upcoming slides, we will dive deeper into the concept and the specific formula used to solve these types of problems. Understanding the concept. Now that we have established that variables can depend on a third factor like time, let's dive deeper into the concept. When we express both x and y as functions of a third variable, which we typically call t, we say that x and y are parametric functions of t. To put this in mathematical terms, we can say x equals f of t and y equals g of t. Now, if our objective is to find the rate of change of y with respect to x, which we denote as di by dx, we can achieve this by analyzing how both variables change relative to our common variable, t. According to the chain rule of calculus, this relationship is defined by a specific formula. Di by dx equals the derivative of y with respect to t divided by the derivative of x with respect to t. However, please keep in mind that this formula is only valid provided that the derivative of x with respect to t is not equal to 0, as division by 0 is undefined. Essentially, what this tells us is that the relative rate of change between two quantities is simply the ratio of their individual rates of change with respect to the common parameter, t. In the next slide, I will guide you through the exact step-by-step procedure to calculate this value. Step-by-step procedure to calculate \frac di dx $. Now that we have established the theoretical foundation and the formula in the previous slide, let us walk through the practical, step-by-step procedure for applying this concept. To find the rate of change of y with respect to x when both are expressed as functions of a third variable, t, you should follow these 5 steps. First, we begin by focusing on the variable x you need to differentiate x with respect to t. This involves taking the given function, x equals f of t, and calculating its derivative, which we denote as dx over dt. Second, we perform a similar operation for the variable y differentiate y with respect to t by calculating the derivative of the function y equals g of t. This will give us the value for dy over dt. Third, we apply the chain rule formula that we discussed earlier. You will take the results from the first 2 steps and substitute them into the formula, where the derivative of y with respect to x is equal to the derivative of y over dt divided by the derivative of x over dt. Fourth, once you have substituted these values, you must simplify the resulting algebraic expression. Simplify the fraction as much as possible to obtain the final, most concise expression for the derivative of y with respect to x. Finally, check if the problem requires the rate of change at a specific moment. If a particular value for t is provided, substitute that value into your simplified expression to determine the instantaneous rate of change at that exact point. To see how these steps work in a practical scenario, we will now move on to a real-world example involving the motion of a particle. Real-world example, motion of a particle. Now that we have established the theoretical framework and the step-by-step procedure, let us apply these concepts to a practical, real-world example involving the motion of a particle. Consider a scenario where a particle is moving across a two-dimensional plane. In this case, its position is defined by 2 different coordinates that both depend on time, which we represent as t, measured in seconds. First, we have the horizontal position, x, which is defined by the equation x equals 3t squared. Second, we have the vertical position, y, which is defined by the equation y equals 4t cubed. Our goal is to determine the rate of change of the vertical position y with respect to the horizontal position x, which is mathematically denoted as dy by dx, specifically at the instant when time t equals 1 second. As we move to the next slide, we will use the chain rule formula we discussed earlier to solve this step-by-step. Step-by-step solution. Now, let us apply the step-by-step procedure we just discussed to solve the particle motion scenario from the previous slide. Starting with step 1, we need to find the rate of change of x with respect to t given that x equals 3t squared. We differentiate this function with respect to t, which gives us 6t. Moving to step 2, we perform a similar operation for the vertical position. Given that y equals 4t cubed, we differentiate it with respect to t to get 12t squared. Now that we have both individual rates of change, we proceed to step 3 and apply the chain rule formula. As we established earlier, the rate of change of y with respect to x is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. By substituting our previous results, we get the fraction 12t squared divided by 6t. In step 4, we simplify this algebraic expression. 12 divided by 6 is 2, and t squared divided by t simplifies to just t. Therefore, the simplified expression for the rate of change of y with respect to x is 2t. Finally, in step 5, we evaluate this result for the specific moment in time mentioned in the problem. By substituting t equals 1 into our expression, 2 times 1 equals 2. This gives us our final numerical answer, which we will now use to draw our conclusion in the next slide. Conclusion. Now, let's wrap up the example we just worked through. Based on the step-by-step calculations we performed in the previous slide, we can conclude that at time t equals 1 second, the rate of change of the vertical position y with respect to the horizontal position x is 2. In practical terms, this result tells us that, at this specific instant, for every 1 unit the particle moves horizontally, it moves 2 units vertically. Now that we have successfully solved this problem, let's move forward and discuss some common mistakes to avoid so that you can apply this method accurately in your future exercises. Common mistakes to avoid. Now that we have walked through the practical example of the particle's motion, it is important to discuss some common pitfalls to ensure you don't lose marks on simple errors. Let's look at the common mistakes to avoid. First, be mindful of the incorrect ratio order. A frequent error students make is placing the derivative of x with respect to t in the numerator and the derivative of y with respect to t in the denominator. To avoid this, always remember that since our objective is to find the rate of change of y with respect to x, which we denote as dy by dx, the derivative of the top variable, y, must always be placed in the numerator. Secondly, do not ignore the condition that the derivative of x with respect to t must not equal 0. Mathematically, the formula becomes undefined if the denominator is 0. In a physical context, such as the motion example we just solved, this occurs when the variable x is momentarily stationary. Finally, be careful not to forget the differentiation step. Some students mistakenly divide the original functions y and x, essentially calculating y over x, instead of dividing their derivatives, which is dy by dt divided by dx by dt. Always ensure you have differentiated both functions with respect to time before you plug them into the chain rule formula. By keeping these 3 points in mind, you can ensure your calculations are accurate. Now, let's move to the final slide to summarize the key takeaways of this topic. Key takeaways. To wrap up our lesson, let's go over the key takeaways to ensure you have a solid grasp of this concept. First, remember that the chain rule allows us to determine the rate of change between 2 different variables, such as x and y, in cases where they are both linked by a third parameter, which is typically time, denoted as t. To do this, we use the formula where the derivative of y with respect to x is equal to the derivative of y with respect to t, divided by the derivative of x with respect to t. As we saw in our particle motion example, this method is incredibly practical. It is used extensively in physics and engineering whenever multiple quantities, such as positions, volumes, or pressures, are all changing simultaneously over time. Finally, always keep in mind the physical meaning of your result. The value of the derivative of y with respect to x represents exactly how much the variable y changes for every 1 unit change in x at that specific instant.